Well, yesterday we did our last day of derivatives. Today we're going to finish up our last day of integrals. And then from the remainder of the time, it's really just going to be applying those things we've learned. So yesterday we got our last 6 derivatives. Today we get our last 3 integrals. So there's only 3. So first up, let's write a little something here, just to make sure we are all kind of on the same page here, because I'm going to use a little shorthand here. Let's let u be equal to f of x, and let d of u be equal to f of x dx. So u's equal to f of x, and then we're going to let the differential du be equal to f of x dx. And if we do that, we end up getting our final 3 integrals. And you're going to notice something probably about these integrals. I should have added one more thing to that, actually. I'm going to go up there and do that here in a second. But let's finish this up first. Arc sine. Also, let a be any real number. There we go. And let's see here. Du is equal to over a squared plus u squared equals 1 over a arctangent u over a plus c. And our last integral of the year is du over u times u squared minus a squared equals 1 over a arcsecant, the absolute value of u over a plus c. So notice we don't have our cosine, cotangent, cosecant on these ones, just the non-cos. So how can you tell which one's which? Well, first of all, for tangent, there's no square root, right? For arcsine, underneath the square root, we're going to have our function. Lied. We're always going to have a number minus a function. And again, the number will be squared and the function will be squared. Whereas arcsecant, it's always going to be function minus number. It's not that there's a number out in front of the radical. We're going to see that sometimes there's not, actually. And we have to end up creating it there. But it's what happens underneath the radical. If it's number minus function, it's arcsine. If it's function minus the number, then it's arcsecant. And if there is no radical, there is no square root, then it's arctangent. So let's start off here, and we're just going to go through and write a couple of integrals. So I'm going to write a few up here, but before we do them, we're going to actually do a quick example of them to make sure that we all kind of are on the same page here. That was supposed to be underneath parentheses. Sorry about that, friends. So 4 plus x to the 4th dx. And we're going to do this one right here. secant squared of 3x all over tangent of 3x and tangent squared of 3x plus, minus 1. So these are the three you guys are going to try first. But let's see how this whole thing plays out. To begin with, let's try, that was weird. Let's try 1 over 49 minus x squared. So we're looking at this here. It's not a power rule because the derivative of this inside function is negative 2x. And if you notice, there's no x up here. It's not a natural log, so that it is going to be an arc sine. And we'll go into more about how to tell which of the three it is tomorrow. But this is an arc sine. So one of the things that usually helps out is to just try to figure out how to balance up the equation. So always take the number and make it equal to a squared. Always take whatever the function is underneath the radical and make that equal to u squared. And we just want to go through and figure out, do we have all the pieces? So if a squared is 49, that means a is 7. If u squared equals x squared, then u is x, and du is 1 dx, which, again, we have that. So we have all of our pieces here. So the way this works then is we're just going to pick the function. So this is an arc sine because it's number minus function. Number comes first, 49 comes first. The function is going to go on top. So our function here, whatever u is, the function is x. The number is going to go on the bottom, which in this case is 7, and then plus c. So what I usually recommend when you guys do these is take your time, really make sure that you know exactly what a is and know what u is, and then you can go from there. Why don't you guys go ahead and pause the video, and let's see what you guys can deal with. All right, let's see how you guys did here. So to begin with, I would have started off and I would have said, let's let u be equal to, or u squared be equal to 9x squared. And a squared be equal to 16. Let's make sure that we have all the pieces we need. So that means u would be equal to 3x. We take the square root of both sides. So du equals 3 dx. I'm going to come back to that here in a second. A is 14, or is 4. So when I'm looking at this problem here, I notice that I have this 5 in the numerator. I don't need a 5 there. So I'm going to pull it out. And I have 16 minus 9x squared. And this is, now we get to the part where I have to compare my differentials. So my differential is just 1 dx. Well, I have 3 dx here, so I got to balance it by taking that 3 to the other side. So if I end up doing this now, I can go ahead and make a simple substitution here, and I can substitute in my u values. Since I didn't have it all balanced up, I can substitute my u in now. 1 over 16 minus, so in place of 9x squared, I'm going to plug in u squared. In place of dx, I'm going to plug in 1/3 du. And we're going to go ahead and kick the 1/3 out. 1 over the square root of 16 minus u squared du. So there's my arc sign. I can see it now. I have a 5/3 there out in front times arc sine of u over 4 plus c. And then we got to get our u out of there. So we still are going to use U-substitution. It's not going to go away. I didn't have to use it on our first example there because everything was all balanced up for us. And let's see, what was u again? U was 3x. So there we are. All right. Let's see how you guys do on this next one. All right, here we go. So u squared is x to the 4th. So that means u then is x squared. And du equals 2x dx. A squared is 4. So that means a is 2. Well, on this one, I'm feeling pretty darn good here. I got the x and the dx. Well, we're going to have to do a little bit of work with that. So I'm close to having what I want. I don't quite have everything I want here because I really want to have a 1 over here. But x dx, notice I got 2x dx for my differential. So if I divide by 1/2, then I get my x dx. So that's where my 1 comes from. So now I'm going to be adding a 1/2 dx or du times u squared. So we're going to kick out the 1/2. So these are really just a matter of just matching up pieces and picking the right integral. Du. So we end up then with 1/2 times 1 over a, and our a value was 2, arctangent u over a, so u over 2 plus c. And put it all together, we end up with 1/4 arctangent whatever u is over 2 plus c. In this case, u was x squared. All right. Now don't look at the tan of 3x outside to realize that that's what u is. It is in this case. But I go inside. I can tell this is arcsecant because I have function minus number. This was arcsine because it was 9 or number minus function. This one is function minus number. So this one's going to be our arcsecant. So u squared is tangent squared 3x. So if I take the square root of both sides, I get u equals tan of 3x. And then du is tan of 3x, so that derivative is secant squared of 3x times 3, it's a chain rule, dx. And what do we have for a squared? A squared is 1. That's fabulous because that means that a is 1. I can deal with a real easily. Now, if we're looking at the pieces here again, let's see what we got. I have my u value out in front. I have my square root of u squared minus 1. But I need to have a 1 up here. And right now I have secant squared 3x dx. I need it to be just secant squared 3x times 3 dx. So I got to move that 3 to the other side. So I get 1/3 du. Now my differentials match up. Got a little crowd here on this, didn't it? Just wanted to make sure that we kept all the integrals on that first page there. 1/3 du. All right, so now the 1/3 is going to go out in front. And now I can see the 1 over u times u squared minus 1 du. And now it's fairly easy to see that this is an arcsecant. So you get 1/3 times 1 over a. So my a value was 1. Arcsecant. Remember, on arcsecant, the numerator, the function part, goes in absolute value over a plus c. So that means I have 1/3 when I put it all together. Arcsecant in u was tangent of 3x. Over 1, or just tangent of 3x. I didn't have to put it over 1, plus c. So really, all we're doing on these ones is we're just taking our pieces and we're matching them up to make sure that we can get our integrals for these arcsines and arctangents and arcsecants to pop out. However, sometimes they don't match up quite so well. In other words, sometimes we have to rewrite a little bit. In some couple ways we're going to look at doing that. The first one is to multiply the top and bottom by the same number. Essentially, we're going to be multiplying by 1. And the second way we're going to be doing it is we're going to be adding or completing the square, which is really nothing more when we complete the square, adding 0 to our denominator. And I'm going to show you what I mean by that here in 1 second. So if we come over here and I give you guys a couple integrals. First one I'm going to give you is the integral of 1 over the square root of e squared x minus 9. And if you look at it, the first thing people will usually say is, they'll say this is arcsine because there's nothing in front of the radical. And friends, it's not arcsine. The reason why is, if you look here, remember, we have the function. I'm using f of x, could use u there as well, over or function first, and we have the number second. This is an arcsecant problem. All right, this is an arcsecant problem. What we have to do is we have to figure out how this becomes an arcsecant problem. So let's take a look at what u squared is. U squared is the function value. And if we take the square root of both sides, we get that u is e to the x. Du is also e to the x dx. And I'm going to come back to that here in 1 second. Let's get our a value out here. So a squared is 9. That means a is 3. Well, if you notice on this problem, if we know it's arcsecant, we're missing something in front of that radical. And that thing in front of the radical, that's supposed to be a u value. Up in the numerator is supposed to be du. And if you notice, our u is the same thing as our du. So we could actually take this radical, or take this integral, and multiply it by the same value to get everything to work out and match up. Here's how we do that. If we multiply both the top and the bottom by e to the x and e to the x, we'd end up creating something that we can actually go ahead and balance to create that arcsecant integral. One of my favorite people's in the classroom right now, friends. That was in the middle of filming, we'd have a little conversation. All righty, friends. So we have e to the x over e to the x. So I have e to the 2x minus 9 dx. Now can you see it? Can you see that how the arcsecant kind of bounced out there? Every once in a while, we're going to have to multiply top and bottom by that same value to get it to balance out and create that arcsecant that we're looking for. In this case now, I can tell that my arcsecant, that this is an arcsecant. I know what my u is, I know what my a is, and so now we can go ahead and figure out what that final answer is. We have all the pieces we needed, so I don't have to add anything. So 1 over a arcsecant, the absolute value of u, and technically I don't have to put e to the x in absolute values because, well, e to the x is always positive already, over a plus c. So sometimes, friends, today you're going to have to go through and multiply the top and the bottom of your integral by a certain number. Likewise, sometimes our integral doesn't necessarily match itself up to being what we want it to be. This isn't a power rule because the denominator is only to 1. It's not a natural log because I don't have the derivative of the denominator in the top, in the numerator. So somehow this has to be an arctangent, but it doesn't set up as u squared minus a plus a squared, or a squared plus u squared. So I have to somehow create that. And this is where we're going to get back to that idea. Back we did an integrated 2 and 3, did it in pre-cal, I've done it for 3 years in a row now, and now we get to do it a 4th time. We are going to complete the square. So we're going to take that denominator and we are going to complete the square. Essentially, we're adding 0. Whatever I add in the denominator, I'm going to come back and take it away. We're going to complete the square to turn this into an actual arctangent problem. So to complete the square, we always take the middle number, you divide it by 2, and then you square it. So negative 6 divided by 2 is negative 3, squared is 9. So if I add 9, then I got to make sure to keep this balance down here. I subtract 9. So positive 9, negative 9, I'm really just adding 0. So I haven't really changed anything in any way, shape, or form. And now, once we do that, I have x minus 3 squared Now you can start to see how this, by completing the square, it turns itself into an arctangent problem. Why don't you guys go ahead and finish up from there and see what you end up with. All right, so let's see here. So u squared is x minus 3 squared. So u is x minus 3. And du is just 1 dx. So we have everything all matching up there for the u. A squared is the number, so a squared is 4. So a is 2. I have all the pieces in place here. I don't have to worry about doing a U-substitution. And I can go ahead and do my integral. So 1 over a, so 1 over 2, arctangent of u, and u was x minus 3, divided by a, so divided by 2 plus c. So we've gone ahead and done some integrals of all three. Sometimes it doesn't set up right, and that's okay. Don't kind of get all that too nervous about it. Sometimes we just have to multiply top and bottom by the same number, so multiply by 1. Or we can add 0 to the denominator by completing the square. And by doing either of those two things, we end up rewriting it in such a way that we can now go ahead and integrate. So sometimes that's going to come into play as well. It's not a big deal. You guys have been doing great so far, so you guys will get it. Well, we've done some indefinite integrals. We rewrote to do some indefinite integrals. The last thing we'll probably need to do is let's do some definite integrals now. So what happens if we have a few final problems here to play with? 1 over, let's go with the square root of 4 minus x squared. And well, let's see, let's do root 3, 6 over 9 plus x squared dx. And last, and certainly not least, friends, let's do root 2 to 2 of 1 over x times the square root of x squared minus 1. All right, so first thing I want you guys to do is I want you to just go ahead and try to integrate it. So go ahead and integrate it, and then we'll go from there. Just do the top one, just do the first one. All right, let's see how you guys did. So a squared is 4. That's my number. Notice it's number minus function, so that means this is going to be arcsine. So a is 2, and u squared is x squared. So u equals x, and du equals 1 dx. So we have all the pieces, so no u sub needed. So we're going to go ahead and integrate it. So it's arcsine and it's u, so u is x over a, so u over 2. Our bounds are -1 and root 2. So we plug it in here, friends. Arcsine of root 2 over 2 minus arcsine of -1/2. Now, just like normal trig, we can't leave arctrig as a ratio. We actually have to evaluate it. If we can. If we can't, we'll leave it alone. But if it can be evaluated, we have to evaluate it. So arcsine of root 2 over 2 So real briefly, we're just going to go through here and figure out where these values are at, arc sine. I know I'm getting rid of these ones over here. Think about where arc sine would fall. Root 2 over 2, it would end up right here. And negative 1/2 would be right here. So this is arc sine of root 2 over 2. That was pi over 4. Minus a negative pi over 6. And then the College Board would actually allow us to leave the answer like that, so you don't have to go any further. If you wanted to, you can. So I'll go ahead and go a little bit further with it just to show you what it would look like. If you wanted to go further, you don't have to. You get 6 pi plus 4 pi all over 24. So 10 pi over 24. If you wanted to go further, you can, but you don't have to. So you can leave it as pi over 4 minus a negative pi over 6. All right, let's try the next one here. Do we have all the pieces? Why don't you guys go and pause the video and try this one, and we'll talk about it. All right, let's see how you guys did. No radical, that means this has to be a arctangent. So a squared is 9. A is 3. U squared is x squared. So du, I lied. Let's backtrack. Probably don't want to do du quite yet. Probably just need to do a regular u. U equals x, and du is 1 dx. So I got all the pieces except for I have that extra 6 sitting up in the numerator. So we need to kick that out there real quick. Yeah, we'll use green for this one. So we're going to kick that out there. So now I have my 1. I have my 9 plus x squared. And I have my dx. So I have all the pieces now. So now we can go ahead. So I have my 6 in front. And I have 1 over a, so 1/3 arctangent of u, so x over a. And we're doing it from 3 to root 3. So I have 6 times 1/3 arctangent of 3 over 3. Minus 6 times 1/3 of arctangent of root 3 over 3. All right, so we can evaluate that a little bit. We get 2 arctangent of 1. Minus 2 times arctangent of root 3 over 3. It will be pi over 6, but. So I do have to evaluate the arc values. I'm not going to draw them out this time. You can if you want to. So 2 times pi over 4 minus 2 times pi over 6. And again, if you want to go further than that, you can. It is completely on you. I'm not going to stop you if you want to. But we can actually stop right there. You don't have to go any further. My friends that did go a little bit further, you would have ended up with this. Pi over 2 minus pi over 3, which would have been equal to pi over 6. But again, I would have left it as 2 times pi over 4 minus 2 times pi over 6. All right. Well, I have an x out front. That does not mean this is arcsecant. This is arcsecant because I have a function minus a number. So in this case, u squared is x squared. U equals x. And du is 1 dx. A squared is 1. So that means a is 1. I have all the pieces I need. I don't have to go terribly far with this one. I can go right to integrating it. Don't even have to pull anything out like we did last time. So if we integrate it, this is an arcsecant, so 1 over a. So 1 over 1. Arcsecant of the absolute value of u all over 1. And then I'm going from root 2 to 2. So arcsecant of root 2. My values are already positive, so I don't have to worry about the absolute value anymore. But notice that absolute value, if either of those were negative, it would have made it positive for me. That should have been 2, not root 2. Minus arcsecant of root 2. You can kind of see why I told you guys at the beginning of the year, the only two real huge, the two most important things to remember from pre-cal last year was the unit circle and then also the Arctrig stuff. So arcsecant of 2 then, that would be at pi over 3. Arcsecant of root 2, that'd be pi over 4. And we can go ahead and stop right there. You don't have to go any further. Although if you wanted to go a little further, you can. That would have been pi over 12, but you did not need to go that far. All righty, friends. So that was inverse or integrals of Arctrig. So now we've completed all of our integrals for the entire year. The rest of the time is just applications. See you guys tomorrow.